Now dear student, we are going to discuss question number 4.15, and in this question it is given to you a magnetic field of 100 Gauss is required which is uniform in a region of linear dimension about 10 centimeter and area of cross section about 10 to the power minus 3 meter square. Clear? And this is also given the maximum current carrying capacity of a given coil of a wire is 15 ampere and number of turns per unit length that can be wound around a core at most is 1000 turn per meter. Clear? So now we have to suggest some appropriate design for this solenoid. Clear? So my dear student, you know, if we want to find magnetic field at the axis of a solenoid, this is given by one formula, and that formula we know B equal to mu naught N I. Clear? So if I find from here value of Ni, I can say this is equal to B by mu naught. Clear everyone? So I can say value of B we have 100 Gauss, so I can say this is 10 to the power minus 4. Clear? Value of mu naught we know this is 4 pi into 10 to the power minus 7. Clear? So from here I can say this value we have 25 by pi. Clear? And it is multiplied with 10 to the power 3. Clear? Value of pi we have 3.14. Clear? So if I write here 3, clear, so we can say that is 7 times or 8 times. So because this is 3.14, so approximately I can say here we are getting value Ni, this is approximately I can say 8000 ampere per meter. Clear? Now in this question it is given to you at most number of turns per length or number of turns per unit length that we can take 1000 turns per meter. So I can say here value of current that I will get 8000 divided by I can say 1000. Clear? So from here you can see that we are getting current approximately equal to 8 ampere. Clear? Now actually we have to suggest here a particular design for a solenoid. Now listen carefully. Actually current for the given values, according to given values we are getting current value 8 ampere. Clear? Now let's suppose if we want to increase value of a current. Clear? If I want to increase this value, definitely number of turns per unit length I have to decrease. Clear? So definitely I can say here I have some variation in number of turns per unit length and current. Clear? Because if I decrease number of turns per unit length, definitely I will increase the current that is flowing in that coil. Clear everyone? And I can increase this current from 8 ampere to up to 15 ampere. Clear? So I can say here we cannot suggest a particular design because it depending on the two factor, number of turns per unit length and we can say current. Clear? So if we are decreasing one parameter, other parameter is increasing, so we can say here we cannot suggest a particular design, but yes, definitely here we can suggest a range. Clear? A range in which a range through which we can say a solenoid can be formed. Clear everyone? So this is all about this question. Now student, we are going to solve question number 4.16, and here first we are solving part number E. Clear? In this question it is given to you for a circular coil of radius capital R, number of turns we have capital N, it is carrying a current I, magnitude of magnetic field at a point on the axis at a distance x from its center. This is given by mu naught Ni R square and divided by twice of x square plus R square power 3 by 2. Clear? Now we have to show that this reduces to familiar result for the field at the center of a coil. Clear? Now listen carefully. Now you know what is the given situation here. Let's suppose here we have a coil. Clear? And let's suppose we have number of turns N. Let's suppose current this is flowing in this coil is I. Clear? It is also given, let's suppose radius is R. We are taking here a point on its axis. We are taking a point on its axis like this. Clear? And we can say, can we calculate here value of B? Yes, I can say value of B, this is calculated by mu naught Ni R square divided by, I can say this is 2 times x square plus R square power 3 by 2. Clear everyone? So value of B I am getting here mu naught Ni R square divided by twice x square plus R square power 3 by 2. Clear everyone? So this one. Now if we want to find value of magnetic field at the center, clear? So at center I can say value of x we have 0, yes or no? So when we have x value 0, I can say, let's suppose I am denoting this value as O, clear? So we can say B naught, this is given by mu naught n I r square divided by, I can say this is 2, this is 2, we can say value of x we have 0, so this is 0, or we can say r square power 3 by 2, clear? I can say this is square, this 2 and 2 is cancelled out, so from here we can say value of B naught, this one is given by mu naught n I r square divided by, I can say 2 r, we can say this is 2 rq, clear? 2 rq, clear? From here you can say r square and this one is cancelled out, and from here we can get value of B naught, this is mu naught n I divided by twice r, clear? So from here you can see we are getting same formula of magnetic field at the center of a closed loop or closed coil, clear? So this is all about part number A. Now dear student, we are going to solve part number B of question number 4.16. In this question it is given to you, we have two parallel coaxial circular coils of equal radius capital R, number of turns is given capital N, it is carrying equal current in the same direction, very important, and separated by a distance capital R. Okay, fine. We have to show field around the midpoint between the coil is uniform over a distance that is small as compared to R, and this is given by 0.72 mu naught Ni upon R. Clear everyone? So now we are going to solve this question. So concentrate on a screen. Actually this arrangement is actually known as Helmholz coils, clear? So now concentrate on a screen. Let's suppose I am taking here, this is a coil number 1, clear? Let's suppose I can say this is a center, and from center we have one more coil like this, clear? And let's suppose I can say this is coil number 1, coil first, I can say this is coil number 2, clear? So let's suppose I am taking here midpoint between these two coils, and one more parameter is given to you, the distance between these two coils we have capital R. So if this is a midpoint, I can say this distance we have R by 2, clear? I can say this one is also R by 2, clear everyone? Now I am actually taking here, let's suppose current that is flowing in this direction, that is I, here we also have same current, that is I, clear? Number of turns is same in each coil, and it is also given both are having same radius, that is capital R, clear? Now we have to prove that from the midpoint, from a midpoint, this one, from a midpoint, if we take here a smaller region, in that smaller region magnetic field due to these two coils, it always remains uniform. So let's suppose I am taking here 2 points, let's suppose here we have a point P, and let's suppose this one is Q, clear? So I can say, let's suppose this distance we have D, and we can say this is also D, clear everyone? And we are assuming actually this D is very small compared to R by 2, or we can say capital R, clear? So now first let us try to understand, let's suppose if I find value of magnetic field at point Q due to both coils, clear? We can take here point P also, we can take point Q also, clear? So I am taking here Q, so I can write like this, value of magnetic field at Q. How can we write? Actually first we are writing here a formula. So formula to find magnetic field at the axis of a coil, this is given by mu naught Ni, we can say Ni, this is R square divided by, we can say twice of x square plus R square power 3 by 2, clear? This is a formula. So now I am writing this formula for point Q. So first I am taking here, let's suppose this is coil number 1, this one is coil number 2. So due to coil number 1, I can write like this, this is given by, I am just writing like this, value of B1, clear? I am writing here inside because this will be required for us. So first I can say value of B1 mu naught, clear? I can say mu naught Ni R square divided by, I can say to value of x. So value of q, value of x for point q, we can say this is r by 2 plus d. Yes, so I can say this is r by 2 plus d whole square, clear, plus we can say this is r square and we can say this is power 3 by 2. Clear everyone? Clear? So this is value of B1. Clear? And what is direction of this magnetic field? Direction of this magnetic field, you can say, because both are in same direction. If I am observing from this side, and let's suppose here we have a coil, and let's suppose current is actually flowing in anti-clockwise direction from my side. So I can say if I curl finger like this, thumb will indicate direction of magnetic field. Clear? So I can say here we have direction of magnetic field in this direction. Clear? Now if I calculate value of B2, or we can say magnetic field due to coil number 2. So how I can write? I can say this is mu naught and I can say this is r square divided by, we can say 2. Clear? Now I can write here this value. So this value will be r by 2 minus d. So r by 2 minus d, this one is whole square, plus I can say here value of r square and it is power 3 by 2. Clear everyone? So now we can say if I write here net magnetic field is given by B1 plus B2. Clear everyone? So value of B1 plus B2. Now you can say mu naught Ni r square divided by 2. This one is common. So I can write like this. Clear? And now we can also write like this. This is 1 upon r by 2 plus d. This one is whole square plus r square and we have this power 3 by 2. Clear? And now we can say this is equal to plus 1 upon r by 2 minus d whole square plus r square and this one we have power 3 by 2. Clear everyone? So now we have to just simplify both the equations and we can get easily variation, or we can get value of magnetic field that is very close to this midpoint. Clear? So now listen carefully. I can say value of B net. This is given by mu naught Ni, I can say r square divided by 2. Clear? This one is multiplication. I am writing here bracket. So this is what 1 upon. So I am just opening here bracket also. Clear? So I can write like this, 1 upon r square by 4 plus d square plus rd plus r square. Clear? And we can say this is having power 3 by 2. Clear everyone? Same we can write for this one also, plus 1 upon, I can say r square by 4 plus I can say d square minus rd plus we can say r square and we can say this power we have 3 by 2. Clear everyone? So now I can say value of B net. I can say value of B net. So value of B net, this one given by mu naught Ni r square divided by 2. Now listen carefully. Actually this d is very small compared to r. So d square we can neglect. So this one I can neglect. So I can say this value is 0 and this one is also equal to 0. Clear? So we can say, we can also write like this, 1 upon r square by 4 plus r square. It means I can say this is 5r square by 4. Clear? Plus I can say this value we have rd. Clear? And we can say plus, oh actually we have here power 3 by 2 also. Clear? Plus I can say 1 upon this value we have 5r square by 4 minus rd. Clear? And this one we have power 3 by 2. Clear everyone? So from here we can say value of B net, this one is given by mu naught Ni r square divided by 2. Clear? Now we can say we can take here common 5r square by 4. Yes or no? Yes. So we can take here common. This value is given. I am just writing like this, 1 upon 5r square by 4 and we have this power 3 by 2. Clear? So now how I can write like this? I can say, we can say 1 upon 1 plus RD is already there. I can say this is 4 upon 5 R square and this power is 3 by 2. Clear? Same I can say here plus 1 upon 1 plus, clear, sorry, minus, here we have minus 1 minus, I can say this is RD multiply 4 divided by 5 R square, clear, and here we are having power this one 3 by 2. Clear everyone? So now concentrate. Yes, definitely lengthy question we have, but if you know the concept and you can, if your calculation skill is fast, you can easily solve this question. Clear? So now I am writing here B net. So B net I can say this is equal to mu naught Ni R square divided by 2. Clear? Now I also write here 5R square by 4 and here we have power 3 by 2 also. Clear? So I can write like this, power 3 by 2. Clear everyone? And I can say here we have value, from here we can say R and R, this one is cancelled out. Clear? So 1 upon, I can say 1 plus, clear, here we have value 4D divided by, we can say 5R power 3 by 2, clear, plus I can say 1 upon, same we can write like this, 1 minus 4D divided by 5R power 3 by 2. Clear? So now we can say mu naught Ni R square by 2 and we can say 4 by 5 power 3 by 2 and we can say 1 upon R cube. Clear? Now we can say when this goes to numerator, this becomes minus 3 by 2 and I can say this is 1 minus 4 by 5 into 3 by 2, this is D by R. Clear? Plus I can write like this, 1 plus 4 by 5 into 3 by 2 and we can say D by R. Actually we know 1 plus minus x to the power minus n. Clear? When x is very less than 1, we can say this is equal to 1 plus minus nx. Clear? So now we can write like this, value of B net, this one is given mu naught Ni R square divided by 2. Clear? Here we have 4 by 5 power 3 by 2. Actually here we have R cube, so you can write like this, this is equal to 2R. Clear? Now from here you can see 1 minus, we can say this one is 6 by 5 D by R. Clear? Clear? Then we can say plus this is 6 by 5 D by R. Clear? From here we can say this one and this one is cancelled out. So we have value mu naught Ni divided by twice R. Clear? We can say this is 4 by 5, 3 by 2. Clear? Here we have 2. Clear? So from here you can say 2 and 2, this one is cancelled out. Clear? So now if you solve this equation, clear? If you solve this value, you can say value of B net, this one is given by mu naught Ni divided by R. Clear? And we can see this value we have 4 by 5 power 3 by 2. So if you solve it, approximately you will find here value 0.72 mu naught Ni divided by R. Clear everyone? So like this we can see in Helmholz coils, whenever we have two coils are having same number of turns, same current, same direction, same radius, and we can say distance between two center of a coil, that is also same. At that time we can say they actually shows a uniform magnetic field near about the midpoint of that coil. Clear? And we can see the result is approximately equal to 0.72 mu naught Ni by R. Clear everyone? So this is all about this question. Now we are going to solve this question number 4.17, and in this question it is given to you a toroid has a core. That is non-ferromagnetic in nature of inner radius and the outer radius, that is 26 centimeter. Clear? So my dear student, definitely you know that what is toroid. Clear? So we can say toroid is just like this. Let's suppose here we have inner core like this. Just a minute. Let's suppose we have inner core like this. This one. Clear? So we can say this one we have a core of the toroid, and we can say, let's suppose wire is going like this. So we can say this structure is actually known as toroid. This one. This one. Clear everyone? Now we can say here, this one we can say we have inner radius, clear, and we can say we have outer radius, clear. So we can say inner radius, this one is given by 25 centimeter, clear, and we can say outer radius, this one is given by 26 centimeter, clear. So we can say inner radius we have 25 centimeter, outer radius we have 26 centimeter, and it is given around which 3500 turns of a wire is wound, clear. It means number of turns is given to you 3500, clear everyone. Now in this question it is given, okay, one more thing is given to you, current is given to you, this is 11 ampere, clear. What is magnetic field? What is magnetic field? Clear. So outside the toroid, so let's suppose I am taking here this point, let's suppose I am taking here point number P. Let's suppose we have point P, clear, and let's suppose if I am drawing here a Amperian loop. Let's suppose if I am drawing here Amperian loop like this, clear. So we can say actually this point P, it lies outside this toroid, clear, and we can say from Ampere law we can write like this, integral of B dot dl, this should be equal to mu naught, and important here we have I enclosed, clear. So now when we can say when point P is lie outside, at the time you can say incoming current, or you can say let's suppose from this point if current is going outside, from this point current is going inside. So if we talk about total summation of a current, you will always find 0 at the outside point, clear. It means we can say magnetic field of this magnetic field due to this toroid at any outside point, we always find this is 0, clear everyone? Yes or no? Yes. Now if we talk about inside the core of a toroid, clear, inside the core of a toroid, now we can say it means now we are taking here another point Q, and this Q point lies in a core. So definitely you should know here a formula. Now here we are utilizing this formula, number B, magnetic field inside a core, this is given by mu naught Ni, clear. So we can say B mu naught, value of mu naught we know, this is 4 pi into 10 to the power minus 7 multiplied small n, very very important. Here we will write number of turns per unit length, but number of turns that is given to you 3500 per unit length, you have to write here 2 pi and multiplied with r, clear. So how you will find here r, because inner and outer radius is given to you, so here you will find mean radius, clear. So we can say mean radius is given by, I can say 25.5 centimeter, that is average of Ri and R naught. So this we can say 25.5, clear everyone. So this is number of turns per unit length, and current that is flowing is given to you 11, clear. Now we are going to simplify, we can say pi and pi, this one is cancelled out, we can say this value we have 2. So from here we can say 7000 into 10 to the power minus 7 multiply 11 divide by, we can say, can we write this is 51 divide by 2, yes or no? So now we can actually easily calculate value of magnetic field inside a core, clear. So we can see value of B, this is given by 7 into 10 to the power minus 4, 7 into 10 to the power minus 4 multiply 11 and divided by 51 by 2, clear. From here we can say this is 14 divided by 51 into 11 into 10 to the power minus 4, clear. So now we can see approximately I am taking here, this is 1 by 4 into 11 into 10 to the power minus 4, clear. This is approximately, but this is not an exact, clear. So I can see let's suppose I am taking here this is 1 by 4, so approximately I can say this is 3, clear. So I can say 3 into 10 to the power minus 4 Tesla, clear. So this is a value, we can say this is value of magnetic field inside core of a toroid, clear everyone? Yes. Now if I talk about in the empty space surrounded by a toroid. Clear? So now you can see, let's suppose if I again draw here this type, this is a core of a toroid. We can see if we are talking about at any point that lies inside this toroid. Clear? It means we can see if I draw here Amperian loop, we can say there is no any current element that we find inside this Amperian loop. Clear? So we can say for part number C, we have value of B inside, this should be equal to 0 Tesla. Clear? So now in this question you can see either we are talking about outside point, either we are talking about inside point, or we can say magnetic field is 0. But what about when we are talking about any point, this is inside a core, at that time we can say value of magnetic field, this is given by mu naught Ni. Clear everyone? This one is given by mu naught Ni. Clear? So this is all about this question. Clear to everyone? Now dear student, we are going to discuss question number 4.18, and here we have actually three parts of this question, part number A, B and C. So first we are going to discuss part number A. In this part it is given to you a magnetic field that varies in magnitude from point to point but has a constant direction. Clear? East to west. Clear? Is set up in a chamber. Clear? So now listen carefully. In part number A, it is given a magnetic field is set up in a direction east to west. So let's suppose I am taking this direction is north, this one is south, east and west. Clear? Magnetic field is set up in the direction of east to west. It means let's suppose this is the direction of magnetic field. Clear? A charged particle enters the chamber and travels undeflected along a straight path. Clear? So whenever a charged particle is actually going in a magnetic field and that charged particle goes without any deflection, it means we can say net force acting on that charged particle, this is 0. Yes or no? So whenever a charged particle is having certain velocity, it is having value q. Clear? So when it enters in a magnetic field, we can say value of force, this is given by q VB sin theta, and this should be equal to 0. Yes or no? Because if the net force acting will be 0, at that time that charged particle will move with constant velocity. Clear? So we can say definitely charge it cannot be 0. Clear? We can say magnetic field value it will not 0, because charged particle is in motion, so velocity is also not 0. It means we can say this is only possible when we have sin theta equal to 0. Clear? And at that time we can say theta equal to 0, or either we can say this is 180 degree. It means what is the meaning of this statement? Meaning is very simple. This charged particle is actually going either in the direction of magnetic field or in the direction, or we can say in the anti-parallel or in the opposite direction of magnetic field. Clear? At that time we can say there is no net magnetic field, there is no net magnetic force will act on this charged particle, and we can say it will move without any deflection from one place to another place. Clear everyone? So this is all about part number A. Clear? Now we are going to discuss part number B. In part number B it is given a charged particle enters an environment of strong and non-uniform magnetic field varying from point to point both in magnitude and direction. Clear? So varying from point to point both in magnitude and direction. Fine, very good. And it comes out of it following a complicated trajectory. Now listen carefully. Actually a magnetic field is having varying magnitude of a magnetic field. Clear? As well as it is also having a different direction. So we know whenever a charged particle enter in a magnetic field, listen carefully what I am saying to you. Whenever a charged particle enters in a magnetic field having certain velocity, definitely a certain force will act on that charged particle, and the important part we have, that force that is acting on that charged particle is always perpendicular to its direction of a motion. The charged particle is going from, it can move in any complicated path, no problem, but important part is here, force acting, it is perpendicular to the motion, direction of motion of that charged particle. So what will happen? We can say directly the angle between force vector and the direction of a displacement, we can say it is always 90 degree. It means we can say work done by magnetic force, it becomes 0. Clear? So we can see according to work energy theorem, we can say work done equal to change in kinetic energy. So work done due to magnetic field we have 0. Clear? So we can say initial kinetic energy, this should be equal to final kinetic energy. Clear everyone? So we can see there is no change in final speed we will find, and we can say final speed it will be same as the initial speed. Clear everyone? So like this we can understand part number A and B both. Clear? Now we are going to discuss part number C of this question number 4.18, and in this question it is given an electron travelling west to east enters a chamber having uniform electrostatic field in north to south direction. Clear? So listen carefully. In this question it is given to you an electron travelling from west to east. Clear? So I am assuming here, let's suppose this direction we have east, this one is west, this one is north, and this one is south. Clear everyone? So in this question it is given to you an electron travelling west to east. Clear? An electron travelling west to east enters a chamber. So now you can see, let's suppose I am taking, this is the direction of motion of an electron. Clear? Having a uniform electrostatic field in north to south direction, it means this is given to you, this is direction of an electrostatic field. Okay. Now we have to specify what should be the direction of uniform magnetic field we should have, so that this electron it never deflect, or we can say it will goes on, that is in a straight line. Clear? So now how can we see it? Let's suppose concentrate here. Let's suppose electron is going in this direction, electrostatic field is acting in a vertical downward direction like this. Clear? Because this is north south direction. So we can say, because this is a negative charge, so we can say an electrostatic force will act in this direction. Clear? Upward direction. So I can say this is Fe. Clear? Now let's suppose if I want this electron should move without any deflection, it means I can directly say magnetic force, this should be act in a downward direction, or we can say from north to south direction like this. Clear? And how this will be possible? I can say, let's suppose magnetic field, I am just assuming magnetic field is actually acting perpendicular inward direction. I am saying magnetic field I have perpendicular inward direction. Clear? I have magnetic field perpendicular inward direction. Clear? Magnetic field perpendicular inward direction. Clear? So and I can say electron is actually moving in a right direction. Clear? So I can say force will act in an upward direction. Yes or no? So when force will act in an upward direction, because this is a negative charge, so I can say here force, magnetic force that will act, that is QVB. Clear? Or I can say this is minus times EVB. Clear? It means definitely we can see magnetic field will act in this direction. And if we talk about magnitude, so magnitude wise we can say EVB, it should be equal to EE. Clear? So from here we can say this is a condition of we can see condition of without any deviation, this electron is going through this magnetic field or through this electrostatic field, when velocity of that electron, this is equal to E by B. Clear everyone? So now we can say in this question, what is direction of magnetic field? Direction of magnetic field is perpendicular inward. Clear everyone? So this is all about this question. Now dear student, we are going to solve question number 4.19, and in this question it is given to you an electron emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt. Clear? Enter a region with uniform magnetic field of magnetic field 0.15 Tesla. Clear? So now concentrate on a screen. In this question it is given to you, we have potential difference, let's suppose this is V and this is given to you 2 kilovolt. I can say this is equal to 2000 volt. Clear everyone? And enters a region with uniform magnetic field. So value of B, this is given to you 0.15 Tesla. This is given. Now we have to determine trajectory of an electron when it is actually transfers to its initial velocity. Clear? It means we can say magnetic field is given to you and that electron is actually going in a magnetic field that is perpendicular to velocity vector of electron is perpendicular to magnetic field. Clear? So I can say part A. So when velocity vector is perpendicular to magnetic field, I can say trajectory, we can say this is given by R equal to mv by qb. Clear? Now we can say, because this is electron, mass is given by 9.1 into 10 to the power minus 31. Velocity of electron, this is not given to you. Clear? Divided by charge of an electron, we can see 1.6 into 10 to the power minus 19, and multiplied with, we can say magnetic field. Magnetic field is given 0.15 Tesla. Clear? So now we can say it is multiplied with V. Now in this question our objective is to calculate value of velocity. Clear? So how can we calculate velocity? For that, one hint is given to you. This electron is actually moving due to potential difference. So I can say here that work done, this should be equal to QV, and actually this potential difference providing necessary kinetic energy to this electron. Clear? So from here we can say V square, this is given by 2QV divided by M. Clear? From here you can say, we can write like this, 2 1.6 into 10 to the power minus 19 multiply, I can say this is potential difference. This V denotes velocity and this V denotes potential difference. This is given to you 2000 volt. Clear everyone? And divided by mass of an electron. So I can say this is 9.1 into 10 to the power minus 31. Clear? So from here we can calculate velocity of an electron. This is given by under root of. Clear? I can write like this, 2 into 1.6 into 2 into 10 to the power minus 16 divided by 9.1 into 10 to the power minus 31. Clear? So from here we can say this is 10 to the power minus 31. When it goes to numerator, this becomes 10 to the power 15. Clear? So we can say V is given by 2 into 1.6 divided by 9.1. Clear? 2 into 1.6 divided by 9.1. Clear? And multiplied with 2 and 10 to the power 15. Clear? So now if we solve this expression, and after solving this expression you can actually calculate here velocity approximately. Clear? So I am just saying here what is this value you will get. You will get here 2.65 into 10 to the power 7 meter per second. Clear? So this is velocity vector that you will get. Now you can put this velocity vector in this expression and you can easily get value of we can say radius of curvature. Clear? Or radius of this circular path. Clear? So now we can see, yes, now we can see radius value is given 9.1 into 10 to the power minus 31 multiply velocity vector, this is given to you 2.65 multiply 10 to the power 7 and it is divided by I can say 1.6 into 10 to the power minus 19 multiply 0.15. Clear? This is given. Clear? Now we can say you can put this velocity value here because this will be useful for part number B. So I am writing here velocity V. This is potential difference and this is velocity vector 2.65 into 10 to the power 7 meter per second. Clear? Now we can say here we have all these values, and if you solve it, clear? If you solve it, you will find here value approximately equal to 10 to the power minus 3 meter. You can calculate it. Clear? So from here we can say this value you will get 1 mm. Clear? So now our objective in this question is to find what is trajectory of an electron. So we can say trajectory of an electron, this is, we can say we have a circular trajectory and this circular trajectory is having radius 1 mm. Clear to everyone? So this is all about part number A. Clear? Now if I say what about part number B? So in part number B, it is given to you when velocity vector is when we can say this magnetic field is making an angle 30 degree with initial velocity vector. Clear? So let's suppose I can say here we have magnetic field in this direction. Let's suppose I can say here it is angle 30 degree. Let's suppose here we have velocity vector. Clear? So I can say here we can take two velocity vector, one component that is parallel to magnetic field and other component that is perpendicular to this magnetic field. So I can take this one, this is V cos 30 and we can say this one is what? V sine of 30. Clear everyone? So now we can see definitely whenever there is an angle between velocity vector and magnetic field, definitely we can see path that is followed by a particle, that is helical path. Clear? And we can see in helical path definitely we have here definitely axial displacement also. Yes, or we can say actually in helical path the electron will going like this, so definitely it is having circular radius as well as we can say here axial displacement also. Clear? So now I can see if I find here two components of a velocity, parallel component is given by v cos of 30. Clear? So I can say value of v know, this is 2.65 into 10 to the power 7, and value of cos 30, we have this is under root of 3 by 2. Clear? And we can say v perpendicular, this one is given by, we can say v sine of 30. Clear? So v sine 30 means we can say this is 2.65 into 10 to the power 7, and this value we have, that is half. Clear? So from here you can say if we find here parallel component of velocity and perpendicular, so perpendicular is given by 1.3. Clear? 1.33 into 10 to the power 7 meter per second. Clear? You can calculate it, and we can also find here the parallel component. Clear? So we can say this is meter per second, whatever you can calculate. Clear? But next we can find here what is a radius, of trajectory that is formed by this, or we can say what is radius of this helical path. Clear? Actually this helical path we can say it also form a circular path. Clear? Or we can say an electron is actually having a circular motion, as well as that electron is also going in a axial direction. Clear? So I can say here if I find here radius, I can say here we can write this is v perpendicular upon qb. Clear? Always keep in mind circular path is only because of perpendicular component of velocity. Clear? So now again I can write mass of an electron 9.1 into 10 to the power minus 31. Clear? Perpendicular velocity, this is given by we can say 1.33 into 10 to the power 7, and divided by I can say charge q. So charge q we can say this is 1.6 into 10 to the power minus 19, and multiplied with I can say value b. B means we can say 0.15. Clear everyone? So now if you solve it, definitely you will find here value of radius. Clear? So that radius value is given to you 50.4 into 10 to the power we can say 10 to the power minus 5 meter. Clear? So like this we can say that definitely in second situation a path, or we can say trajectory that is followed by an electron, that is helical one. Clear? And that helical one is having radius we can say 50.4 into 10 to the power minus 5 meter. Clear to you? So this is all about this question. So dear student, we are going to discuss question number 4.20, and in this question it is given to you a magnetic field setup using Helmholz coil is uniform in a small region and having a magnitude of 0.75 Tesla. Clear? So my dear student, do you know what is Helmholz coil? In a Helmholz coil we can say we have two coils. Clear? Having same number of turns, current flowing that is also same, radius of each coil is capital R, distance between these two coil is also capital R. Clear to everyone? So that is known as Helmholz coil. And one more thing, if you find magnetic field, net magnetic field in the midpoint between these two coils, we can say this is almost same. Clear? So now we can see here it is given the value of net magnetic field, this is 0.75 Tesla. So I can say value of B, this one is given by 0.75 Tesla. Clear everyone? 0.75 Tesla. So in the same region a uniform electrostatic field is maintained in a direction. Okay, this is clear to you, this is just a theory. Yes, one more thing is given to you, a single species of a charged particle is accelerated through 15 kilovolt. It means I can say potential difference is given 15 kilovolt. So this is equal to 15 into 10 to the power 3, and this one is volt. Clear? it enters this region in a direction perpendicular to both the axes. Okay, if the beam remains undeflected when electrostatic field is this one. Clear? So electrostatic field is also given to you. So I can say electrostatic field is also given. So actually this is 9 into 10 to the power plus 5. Clear? So I can say value of E, this one is given by 9 into 10 to the power 5, and this is volt per meter. Clear to everyone? Okay. So because in this question it is given charged particle is actually going without any deflection, it means I can say whenever electric and magnetic both field are present, we can say magnetic force, this is QVB, this should be equal to, I can say this is equal to QE. Clear? From here we can say Q and Q, this one is cancelled out. Clear? So from here we can say V, this is given by E by B. Clear? So we can say value of V, this is given by E by B. Clear? Okay. Now electric field is given to you 9 into 10 to the power 5, and it is divided by 3 by 4. Clear? So I can say this is 12 into 10 to the power 5 meter per second. Clear? So this is value of velocity of a charged particle. Clear? So I can say value of velocity, this is given 12 into 10 to the power 5 meter per second. Clear? Now actually we have one more thing. It is given in a question that the charged particle is accelerated. It means whatever the kinetic energy that is gained by that charged particle, it is provided by this potential difference. Clear? It means we can write like this, W equal to QV, and this should be equal to half of mv square. Clear? So from here can we calculate velocity? Yes, we can write like this, or yes, actually can we calculate here value of Q by M? Q by M, this is given by V square divided by 2 capital V. Clear? So now we can put here values. Yes, now we can put here values. So value of Q by M, this is given V square. So velocity is given to you 12 into 10 to the power 10. Clear? And it is divided by, I can say 2 multiply V. So 2 into 15 into 10 to the power 3. Clear everyone? So from here we can say, yes, from here we can say, we can write like this. This one we have 6. So 6 into 12 divided by 15. Clear? And we can say this is 10 to the power 7. Clear? So 6 into 12 divided by 15 into 10 to the power 7. Clear? So Q by M, this is equal to. Clear? So if you calculate it, you can easily get here answer. We can say if you cut by 3, so we can say this is 2, this one is 5, this is 24 by 5 into 10 to the power 7. Clear everyone? So now we can say this is equal to 4.8 into 10 to the power 7. So we can say charge to mass ratio in this question is given by 4.8 into 10 to the power 7. Clear? Now dear student, if I calculate charge to mass ratio for a deuteron. Clear? So I am saying if I am calculating Q by M ratio for deuteron, I can say charge we have for the deuteron, we can say this is 1s2. Clear? And charge is equal to charge of an electron or charge of a proton, I can say this is minus 90. Okay. If we talk about mass, I can say it is having 2. So I can say 2 into mass of a proton 1.6 into 10 to the power minus 27 kg. Clear? So from here you can say we can write like this, this is 10 to the power 8 and divided by, I can say 2. Clear? Actually we have this is 1.67, but approximate I am taking this is 1.6. Clear? So from here I can write like this, value of Q by M, this should be equal to 4.8 into 10 to the power 7. So from here you can say Q by M ratio that we are getting from this calculation is approximately same as the Q by M ratio that we get from deuteron. Clear? So it may be a possibility that this charged particle may be a deuteron. Clear? But actually we have 2 more particles. Clear? Let's suppose if I say He2 plus. Clear? Let's suppose if I say Li3 plus. Clear? So let's suppose if I say we have 2 more particles, He2 plus and Li3 plus. Clear? So for that one, if you calculate Q by M ratio, you will get same answer. That's why we can say that deuteron, it may be a possibility that deuteron may be a charged particle, but it is also a possibility we may have these two particles also. Clear? That's why we can say this answer is not unique. Clear to everyone? That's why we can say this answer is not unique. So hope you understand this question. So this is all about this question. Now dear student, we are going to solve question number 4.21, and in this question it is given to you, we have a straight horizontal conducting rod of length 0.45 meter and mass 60 gram is suspended by two vertical wire at its end. Clear? So now listen carefully. In this question it is given to you, let's suppose here we have, this is a fixed end. Let's suppose here we have a fixed end, this one. Clear? Now let's suppose I am connecting here two strings, or you can say here we have two vertical wires. Clear? Let's suppose we are connecting here. Let's suppose this is a rod. Let's suppose this is rod. Clear? It is given here in this question, length of a rod is 0.45 meter. So L equal to 0.45 meter. This is given in a question. Clear? And a mass of 60 gram is suspended by two vertical wires. Clear? So I can see here mass is also given to you. Mass is given 0. Where is this one? This one. We can say mass is given, this is equal to 60 gram. Clear? So mass is also given 60 gram. It is suspended by two vertical wires at its end. Okay, fine. A current of 5 ampere is set up in this rod. It means current value is given to you 5 ampere. Clear? Now in the first part it is given what magnetic field we should set up here normal to conductor so that tension in the wire becomes 0. Now let us try to understand what are different forces acting on this rod. Clear? So I can see here, we can see here a force is acting, this is mg. Clear? And we can say here a force is acting, that is BIL. Clear everyone? So here mg force is acting, and let's suppose if we apply here magnetic field, I don't know in which direction, but let's suppose if I apply magnetic field, definitely the magnetic force, it should act in a vertical upward direction, so that we can say tension in both the string or wire, it becomes 0. Clear? So if you write here equation, we can write like this, BIL plus 2T, this should be equal to mg. So in the first case, if we want that we want that tension in a wire, it should be 0. So let's suppose I am saying this is 0. So from here you can say BIL, this should be equal to mg. Clear? So from here, can we find here value of B? Yes. So value of B, this one is given by mg divided by, I can say, IL. Clear everyone? So now from here we can say mg by IL. M mass is given to you 60 gram, so 60 into 10 to the power minus 3. Value of G we have, that is 10, and it is divided by, I can say, current we can say this is 5, and we can say length of a conductor is given 0.45 meter, or we can say 45 into 10 to the power minus 2. Clear? From here we can say this one all are cancelled. Clear? So we can say this is 12. So from here we can say 12 divided by 45, or I can say this is 4 divided by 50. Clear? So from here can we calculate value of magnetic field? Yes or no? Yes. So from here you can say we are getting value of B. This should be equal to 4 by 15, or we can say this is 0.26 Tesla. Clear everyone? So like this we can calculate value of magnetic field so that tension in this wire becomes 0. But the important part is here, what is direction of this magnetic field? Clear? So let's suppose I am assuming current that is flowing in this conductor in this right direction. Clear? Now let's suppose, listen carefully what I am saying to you. Let's suppose here we are talking about positive charges. Let's suppose if I apply magnetic field is perpendicular inward. Clear? Thumb indicates direction of a motion. At the time I can say this palm indicates direction of a magnetic force. Clear? Actually we can use either Fleming left hand rule, or we can utilize right hand palm rule. So if we utilize right hand palm rule, I can say in this situation we are having magnetic field perpendicular inward. Clear everyone? So the answer of this question we have, that is 0.26 Tesla. Clear everyone? Now listen carefully. Now we can say in part number B, it is given to you what will be total tension in a wire if direction of a current is reverse. Now listen carefully. If we reverse here direction of a current, let's suppose now in this direction towards left direction. So what will happen when we change the direction? We can say magnetic field is perpendicular inward, thumb is indicating direction of a current or motion, or we can say velocity, and we can say now bill will act in a perpendicular downward direction, or we can say vertically downward direction. So from here we can say here BIL also act in a vertical downward direction. Clear? So now our objective in this question is to calculate total tension. So from here we can say, we can write like this, value of tension 2T. Clear? We have to calculate here total tension in a wire. Clear? So I can say 2T, this is given by, I can say BIL plus, I can say this is mg. Clear to everyone? So now we can say, can we calculate here value this? Yes, I can say 2T, this is given by BIL and mg. Clear? Now we can calculate, yes or no? Yes, definitely we can calculate. So how can we calculate? If we can see from the last, if we talk about part number A, in part number A you can say mg is equal to bill. Clear? Due to which we are getting tension 0. Now let's suppose we can say here, you can say, actually we can also write like this, this is equal to twice mg. Why? Because BIL is equal to mg. We are not changing magnetic field, we are not changing current, actually we are just changing direction of a current, but magnitude wise mg and bill it should be same. Clear? So from here we can say this one and this one cancel out. So value of tension T. Clear? Value of tension T, this is given by, I can say m. So mass is given to you 60 gram. So 60 into 10 to the power minus 3, and value of G I am taking, this is 10. Clear? So from here we can say 6 into, I can say this is 10 to the power minus 1. Clear? So value of tension that we are getting, this is equal to 0.6 Newton. Clear? So actually this is a value of tension T, or we can say tension in a single wire. Clear? But what is our objective in this question? Our objective in this question is to calculate total tension in a wire. Total tension means I can say this is 2T, so I have to multiply it with T. I can say approximately we will get this is 1.2 Newton. Clear to everyone? So this is all about this question. Now dear student, we are going to solve question number 4.22, and in this question it is given to you the wires which connect the battery of an automobile to its starting motor of carrying a current of 300 ampere. Clear? So try to understand this question. Actually it is given to you, let's suppose we have two wires. Clear? And let's suppose these two wires are connecting, we can say a battery of an automobile. Clear? And current that is flowing in both the wire is same. Clear? Actually a battery is connected in between the wires like this. Clear? So now we can say actually a current is flowing, so we can say current is flowing, this is 300 ampere, and here we can say, let's suppose this is I2, this is also 300 ampere, this is I1. Clear? Now in this question it is given, we have to calculate force per unit length between wire when they are 70 centimeter long. It means length is given to you 70 centimeter, as well as distance between these two wire is given 1.5 centimeter. Clear? So my dear student, actually we know one formula, the force per unit length. Force per unit length, this is given by mu naught I1 I2 divided by 2 pi d. Clear? So from here we can calculate force per unit length. This is given by value of mu naught. Value of mu naught we have 4 pi into 10 to the power minus 7 and multiply, I can say I1 I2. So value of I1 is given 300 into, I can say this is also 300, and divided by, I can say 2 pi d. So we can say 2 pi, and distance is given to you 1.5 into 10 to the power minus 2. Clear? So from here we can say this one and this one cancelled out. Clear? We can also write this 1.5, this is equal to 3 by 2. Clear? So I can say this is 3 by 2. from here we can say this 2 is actually we can say this 2 will move in a numerator. So 2 into 10 to the power minus 7, clear. I can say this one is cancelled out, so this is 100, clear. 100 into I can say this is 300 and divide by 10 to the power minus 2, clear. From here we can say this one and this one cancelled out, this is 10 to the power minus 5, clear. So we can say this is 2 into 3 into 10 to the power minus 1, clear. So from here you can say force per unit length, this is given by 0.6 Newton per meter. But what is our objective in this question? Our objective in this question is to calculate what is force per unit length. Okay, this one, clear. So force per unit length here, it is given by 0.6 Newton per meter, and these forces are attractive or repulsive. We can say because current that is flowing in both the wires are having in an opposite direction, so definitely they are having repulsive in nature. How can we see? Let's suppose if we are talking about this wire number 1, you can say let's suppose we have we want to find magnetic field at any point this wire, on this wire. I can say if we say let's suppose this thumb indicate direction of a current, so magnetic field in this direction, clear. Now we can say what is direction of a force acting. I can say if these fingers indicates direction of magnetic field, thumb indicates direction of a current, I can say force will act here like this, force acting on 2 by 1, clear. Similarly if you find for number 1, you can say here you will find F12. Now you can say here these two forces are repulsive in nature, clear everyone. So we can say for the last we have answer repulsive, clear. So this is all about this question. Now dear student, we are going to discuss question number 4.23, and in this question it is given to you a uniform magnetic field of 1.5 Tesla exists in a cylindrical region of radius 10 centimeter. Okay, fine. Its direction parallel to axis along east to west, and a wire carrying current of 7 ampere in north to south direction passes through this region. Okay, what is the magnitude and direction of force on the wire if number A, the wire intersect axis? So actually you can see here in this question it is given we are having a uniform magnetic field that is exists in a cylindrical region. Radius of that cylindrical region is also given to you, and direction of magnetic field it is given that is along the axis east to west, clear. Now it is also given we have a wire that is actually going through this cylindrical region and having current 7 ampere and from north to south direction, fine. So let us try to solve this question. Actually we have 3 parts of this question. Now we have to provide here answer of each and every part, clear. So now concentrate on a screen. Now dear student, now we are going to solve this question. First of all, if I am saying to you, let's suppose if I draw here a diagram, let's suppose I am assuming this is a cylindrical region. Listen very carefully, clear. Cylindrical region. Let's suppose I am saying this is direction north 1, this is south direction, clear. And I can say let's suppose this direction is east and this one we have west direction, clear. Actually what will happen here, this is west direction, this is east direction, and I am saying this is north and south. Actually this north south direction is what you can see like this. This is east direction, this one is west direction. I am saying this one is north direction and this is south direction, clear to you. So if I am showing it like this, it means you have to assume here actually we have a wire, this is not like this, this wire is like this, clear. So I can say this is east, this is west, this one is north and this one is south, clear. So now we are going to solve first part number A. Now concentrate here. In this question it is given to you a uniform magnetic field exists in a cylindrical region from east to west. So I can say here direction of magnetic field it is given to you in this direction, and magnitude of this magnetic field it is given 1.5 Tesla, fine. It is also given here it is having radius. So I can say this cylindrical region having radius 10 centimeter, fine. Its direction parallel to, okay, direction is clear to a wire carrying a current of 7 ampere in the north to south direction. So now we can say let's suppose here we have a wire and that is wire that is going like this, actually this wire is also passing through the, we can say, axis. We can say actually it intersect axis or not, it will we will decide from this particular parts. Clear? So in this question it is given to you simply a wire carrying a current 7 ampere from north to south direction. So let's suppose I am saying this is a wire, clear, and this wire is going from north to south direction and current is given to you, that is 7 ampere. Clear? Now we have to find what is magnitude and direction of a force, number A, when the wire intersect axis. So let's suppose I am saying you can see you can observe like this. Let's suppose this is cylindrical region. Clear? In this cylindrical region we have a wire like this. Clear? And current is going from north to south direction, and it is also passes through, it is also intersecting axis. It means I can say this wire is passing through, if I am observing from this side I can see circle, so it is passing through the center of circle. Clear? So now we can say our objective here is to find first magnitude. So I can say F, this is given by BIL, that is sine of theta. Clear? You can also write like this, this is I L cross B. Clear? We can say I, this is L cross B. Clear? Now value of I is given to you in this question, that is 7 ampere. Clear? So I can say 7, or you can say, you can place here value 7 multiply. What is value of B? Value of B, it is given 1.5. Now important part, what is L? Clear? L is, we can say, length of a wire that is inside this cylindrical region. Clear? Now you can say actually this wire is intersecting axis, it means we will take length along the diameter. Clear? So now we can say we will take this length, let's suppose this length is L. Clear? And this length we can say that L equal to twice R. Clear? So this 2 multiply, what is value of R? R is given to you, that is 10 centimeter. So 10 multiply 10 to the power minus 2. Clear? Now you can say what is theta? Theta is angle between what? Because this is L cross B, so we can say this L and this B both are perpendicular to each other. So I can say this is sine of 90. Clear? So from here you can write like this. This is equal to 20 into 10 to the power minus 2. So 2 into 10 to the power minus 1. Clear? Multiply, I can say 15 by 10 multiply 7. Clear? So from here you can say this is 30, or I can say that is 10 divide by 100, and this one is equal to 2.1 Newton. Clear? So we are getting here force acting on this wire, that is equal to 2.1 Newton. Why force is acting? Because whenever we place a current carrying conductor inside a magnetic field, it always feel a force. Clear? So this is all about part number A. Clear to you? Now we are going to discuss part number B. If this wire is turned from north south to northwest or northeast direction. Clear? Now let us try to understand what will happen in second situation. Clear? Let's suppose if I draw again a new diagram, it will be better for us. So yes. Now you can say, let's suppose this is same cylindrical region that we are assuming. Clear? I can say this is direction, that is direction north and south. This is north one and south one. You can see now this direction is perpendicular to this screen. Clear? Direction of B, that is given to you from east to west. Clear? Now it is given. Now we are changing up little bit. What is the change? Now we are placing this wire north south or northwest direction. It means, let's suppose I am placing like this. Here we have northeast direction. I am placing in northeast direction. Clear? Whenever I am saying northeast direction, actually what parameter will change? Is current changes? No. Current is already given to you. Current is flowing in this direction, that is 7 ampere. Clear? But we can say length of that wire inside this cylindrical range, that changes. Clear? So we can write like this, F equal to, this is actually part number B. Clear? So F equal to, I can say this is BIL sine of theta. Clear? Value of B. Value of B we can see from this slide. Value of B we have, that is 1.5 Tesla, R we have 10 centimeter. So 1.5 Tesla, 7 ampere current, length. Length we can say, actually let's suppose I am saying this length is what, L dash. Clear? From here you can see, if I draw here perpendicular. Clear? If I draw here a perpendicular. Clear? I can say this angle we know, that is 45. clear. This angle is 45, I can say this one is 45, this one is also 45, clear. We know this value we have, that is L, clear. So can we find here L equal to, this is L dash cos of 45, clear. I can say this angle is 45, so L equal to L dash cos of 45. So from here I can write L dash equal to L upon cos of 45, clear. Value of L is what? We can say this is equal to twice R, clear. Twice R divided by, I can say that is 1 by root 2. So this is equal to 2 root 2 and multiplied with R, clear. 2 root 2 multiplied with R. So 2 under root 2, what is value of small r, clear. Small r value, this is given to you, yes, that is 10 centimeter, clear. So I can say we can convert into meter, so this is equal to 10 to the power minus 1. So now we can say this is 1 by 5 multiply, I can say 1.414, clear. Yes or no, we can write like this, clear. Or you can say correct, this one is correct. Or you can also write like this. This is just the value of L dash, clear. So we can place this value here better, clear. So now I can place this value here. Value of L, this is equal to 2 under root 2. Actually here we will take not L, this is L dash, clear. So this is L dash and I can say sin theta. So 2 root 2, clear. And I can say this is multiply 10 to the power minus 1 and I can say this is sine of 45, clear. Sine of 45. So from here we can write force acting on a current carrying wire. This one is given by 1.5 multiply 7 multiply 2 root 2 multiply 1 by 10 multiply 1 by root 2. I can say this one and this one cancelled out, clear. Or we can say this one we have 10. So from here we can say this is 14. So 14 multiply 15 divided by, I can say this is 100, clear. So if you multiply it, you can see F is given by 210 divided by 100 and we are getting magnitude, this is 2.1 Newton, clear. Actually can you find here direction? Yes. Now we can say, let's suppose these fingers are representing direction of magnetic field, clear. Let's suppose my thumb, this indicating direction of current. So definitely I can say direction of this palm is representing force acting on that conductor. It means definitely I can say here, if I show here direction of force acting, that is vertically downward direction, clear. So now we can say this is magnitude. If I write here direction, that is vertically downward, clear to everyone? Yes. Now let us try to understand part number C, clear. Now I am showing to you part number C. Part number C. Let's try to understand what is part number C. The wire in north-south direction is lowered from the axis by a distance of 6 cm. Clear? Now listen carefully. Actually, this part will be little bit confusing for a student, but actually this is very simple part. Let us try to understand. Let's suppose we have this cylindrical region. Let's suppose this is cylindrical region. Clear? In this cylindrical region, you know, I can say this is center. Clear? And you say this is north and south direction. This is clear to us. But this situation will be there where in part number A and B it is given this wire that is along north south direction, it is actually passing through, it is actually intersecting axis. But now it is given here that we are lowering this wire by 6 cm. It means now you can say if you are placing north south direction wire, I can say this will be like this. Clear? But if you are lowering by 6 cm, it means I can say you can lower it like this. Clear? So it means if you observe from this side, how can you see this diagram? Listen carefully. Let's suppose because if you are observing from right side, you can see this is a circular part. Clear? I can say this one is center. Clear? I can say this one is center, and actually initially you can see this is north direction, this is south direction, and wire in this direction. Now I am lowering this wire by 6 cm. It means I can say actual this is the direction of it is actual position of wire. Clear? So I can say, let's suppose this is north, this is south. I can say current is flowing in this direction. You know very well that is 7 ampere. Clear? But from here you can say this distance is what? This distance is given to you 6 cm. I am assuming from here this distance is x. Definitely this one will be also x. Clear? Now if I join here these two lines, I can say definitely this is equal to radius, so 10 centimeter, 10 centimeter. Can we calculate here value of x? Yes. So how can we calculate? We can apply Pythagoras Theorem. So I can say this is given by 10 square, this is equal to x square plus 6 square. Clear? So from here I can say x square, this is given by 10 square minus 6 square. Clear? We can also write like this is 100 minus 36, 64, or we can say this is 8 square. Clear? So value of x we can say 8 centimeter. Now you can say, sir, why we are writing this value? So listen carefully. Now we will find here total length of this wire that is present inside this cylindrical region. Clear? So I can say the part of that wire that is present in this cylindrical region is this one. Yes or no? Clear? So I can say from here value of L that is written by 2x. Clear? That is 2x, and I can say this is equal to 16 centimeter. Clear? Definitely current is flowing in this direction, no problem. Clear? And we can say magnetic field is, let's suppose this is north, so you can say this one east, this one is west. So I can say in this diagram magnetic field is perpendicular inward like this. Clear? So directly we can say angle between this wire, or we can say this current, or we can say this L and this magnetic field, that is 90 degree. So I can say force acting, that is given by BIL sine of theta. Let's suppose I am taking this L double dash. Clear? So from here value of B we have 1.5 Tesla, this is 7. What is value of L double dash? 16 centimeters. So 16 into 10 to the power minus 2, and I can say perpendicular. So we can say this is equal to sine 90. Clear? So we can say this is equal to 16. So we can say that is 24 multiply 7 into 10 to the power minus 2. Clear? So 27 multiply, I can say here we have 168. Clear? And it is divided by 100. So from where we are getting answer 1.68 Newton. Clear? And what about direction of a force that is acting? So I can say these fingers are representing direction of magnetic field, this one is representing direction of current. So I can say again we have vertically downward direction. Clear? Vertically downward direction. Clear to everyone? Yes or no? So this is all about this question. Now dear student, we are going to discuss question number 4.24, and in this question actually we have A to F, total A to F part. Clear? So now let us try to understand what is this question and what is our objective in this question. Clear? So we can say in this question it is given to you a uniform magnetic field of 3000 Gauss is stabilized along positive z direction. Clear? So it is given here, I am writing here value of B. I am writing here in form of vector. So magnetic field is acting 3000 Gauss. So 3000 Gauss, you can convert it into Tesla. If you are multiplying here 10 to the power minus 4, so at that time we can say this is equal to 0.3 Tesla. Clear? Okay. Now it is given here, this is in a z direction. So how can we write in vector form? I can say this is 0.3 and this is in positive z direction. So I can say this is equal to kk. Clear? Now a rectangular loop of side 10 centimeter and 5 centimeter. So I can say magnitude of area, it is given by directly we can say 10 multiply 5, this is equal to centimeter square. Clear? So from here I can say this is 50 centimeter square. Clear? 50 centimeter square, it carries a current of 12 ampere. So I can say it carries a current of 12 ampere. Fine. What is torque acting on this loop? Now different cases will be shown to you here. So first I am talking about part number A. In part number A, what is value of torque? So I can say torque, this is given by one formula, torque equal to we know that is bina sin theta. Clear? So we have here only one number of loop. So I am saying BIA sine of theta, or you can also write like this, this is I A cross B. Clear? Now you can say how we will find here direction of area vector. So you can see here direction of current in anti-clockwise direction. So if you curl your finger like this, thumb indicate direction of area vector. Clear? So area vector direction is always perpendicular to this surface. So I am saying here this area vector we can write like this in vector form. In vector form I can say this is 50 into 10 to the power minus 4, this one is magnitude, and I can say this is Ik. Clear? So now I am writing here torque. So torque value I can say value of I we have 12. Clear? A 50 into 10 to the power minus 4 I cap cross value of P 0.3 K cap. 0.3 K cap. Clear? So if we talk about magnitude, we can say this is 600. 600 multiply 0.3. It means I can say 180. Clear? So from here you can say 180 into 10 to the power minus 4, and I can say I cross K cap. Clear? I cross K. I cross K is what? Minus J cap. So from here we can say this is equal to minus 1.8. Clear? I am writing 1.8 into 10 to the power minus 2, and this one is J cap. Clear? So this is value of torque. You can see here value of torque is having 1.8 into 10 to the power minus 2 Newton meter, that is magnitude. And what about direction? Direction is along negative y direction. It means in this direction. Clear to you? Yes or no? So this is all about part number A. Similarly, we are going to discuss here part number B. Okay, actually we have one more thing here. What about net force acting? Clear? So net force you can see here. Actually we know formula of force. Clear? What is that formula? F is given by, that is Bil sin theta, B-I-L sin theta. I can say that is I, L cross B, L vector cross B vector. Clear? Now you can say whenever I am saying this is B-I-L sin theta, and theta is angle between L and B. So you can say whenever the current element that is parallel to B, you can say angle is 0 or 180. So we will find sin 0, sin 180, that is 0. Clear? But what about this one? Definitely I can say here angle between B and L, that is 90 degree. So definitely force will act, that will be maximum. But what about direction? Now you can say both wires are parallel and current is going in a opposite direction. So definitely I can say, let's suppose on this wire force is acting in upward direction. On this wire this force will act in downward direction. Clear? So definitely these forces will be cancelled out. So finally net force that we are getting here for this loop, this is equal to 0 Newton. Clear to everyone? Done. Now if I talk about case number B. In case number B, again our objective is same, to find torque. Torque is given by I can say that is B, we can say this formula I A cross B. Clear? So I A cross B, A cross B. Now here what is area vector? Definitely you can say area vector is same. Clear? So value of I. Clear? I can say this is 50 into 10 to the power minus 4. Clear? This is magnitude, and direction of area, this is Ik. Clear? Cross. What about B? B is given to you in this question. Yes, we can say 3 into 10 to the power minus 1 or 0.3, and in direction of Kk. Clear? So from here we can say value of I is also known, that is 12. So 12 into 50 into 10 to the power minus 4 into 0.3 multiply, I can say I cross Kk. Clear? Now I cross K equal to what? Minus J. Clear? So I can say minus, this is 600 into 10 to the power minus 4, this is 3 by 10, and this is Jk. It means we are getting same value. Clear? As the previous one. Clear? So from here we can say this is equal to minus 180, or we can say 1.8 into 10 to the power minus 2 Jk. Clear? So this is value of a torque. And what about net force? Again you can say these two elements are parallel to magnetic field, net force is 0. Clear? And what about these? These two elements are having current in an opposite direction. So definitely whatever the direction of force we will get, that force will be cancelled out. Clear? So again we can say net force, this is acting here, that is equal to 0. Clear to everyone? Yes. Now here I am talking about this part number C. Clear? In part number C, again our objective is same, to calculate torque. Torque we can say that is equal to I A cross B. Clear? Now you know value of I we have 12, but what about A, area vector? Now we can say from here, you can say if you curl your finger like this area vector will be in this direction. So definitely I can say this is in opposite direction of y. Yes, so we can say this is 50 into 10 to the power minus 4 and direction, this is minus of j cap cross. What about B? B is same 0.3, this one is k cap. Clear? So from here we can write like this, 12 into 50 into 10 to the power minus 4 into 0.3, yes, minus j cross k we are getting. So j cross k equal to what? I cap. So again we are getting same magnitude, minus 1.8 into 10 to the power minus 2, this is magnitude and this is I cap. Clear? So this is all about value of torque. But what about force? Now you can see these two conductors or these two elements are in the direction or parallel to magnetic field. So force acting is 0. And if we are talking about this one, this L vector and this L vector is perpendicular to B. So definitely maximum force will act, and direction of current is opposite. It means we can say whatever force will act here, magnitude wise they will be same, but in direction they will be opposite, so they will be cancelled out. Again you are getting here value of net force, this is equal to 0 Newton. Clear to everyone? Yes. Now let us try to solve this part number D. In this part it is given to you what is the direction of area vector. So directly you can say this is direction of area. Clear? Clear? And what about B? Clear? So now we can say B in this direction. Clear? So now we can say what is angle between B and A, because our objective here is to find torque. Clear? So torque, I can say this is given by I B cross A. Clear? So value of I we know this is 12, 50 into this is A cross B. A cross B. Clear? This is A cross B. A cross B. Clear? 50 into 10 to the power minus 4. And what about area vector? Area vector in which direction? Now you can say actually this is lie in YZ plane. Clear? You can say this is lie in a YZ plane. You can see this is Y, this is Z, and this one is XY plane. Okay. So actually this lie in Y and XY. So if we talk about area vector direction, now you can see area vector direction whatever we have, it is perpendicular to Z axis. It means I can say angle between area vector and B vector, this is equal to 90 degree. So directly I can say here this is equal to I A B only, because sin 90 equal to 1. Clear? And multiply 0.3. Clear? So from here we can say again we are getting 12 into 50 into 10 to the power minus 4 into 0.3. Clear? And this is 1.8 10 to the power minus 2 Newton meter. Clear? Now what about net force? So definitely due to these two elements I can say force acting is 0, and from here these two elements current direction is opposite, so net force acting is 0. So directly you can say here net force, this is equal to 0 Newton. Clear to everyone? Yes. Now we are going to discuss this one, that is part number E. In part number E, again if we find here torque is given by I A cross B. Clear? Now you can say in this time this loop is actually placed in XY plane. So if you curl your finger, thumb will indicate in the direction of Z. Clear? So I can say here we can write like this, 12, 50 into 10 to the power minus 4, and this is direction K cap. Clear? And from here we can say this is 0.3 K cap. Clear? Now you can say finally you will get here K cross K. K cross K equal to what? That is 0. So here we are getting magnitude of this torque, that is 0 Newton meter. Clear? And what about force? Definitely you can say here each element of this current carrying loop, clear, it is having perpendicular to this B. It means I can say, let's suppose force acting on this wire in this direction, let's suppose. So on this wire it will act like this. Here let's suppose force acting like this, here the force will act. Clear? So I can say for if we have a uniform magnetic field, clear, and we are having closed loop, at that time I can say here value of net force directly you can say here 0. Actually here one more question is asked here, what is force on each case? Clear? And which case corresponds to stable equilibrium? Now you can see in this case we are getting theta 0. Clear? Theta is what? I can say angle between area vector and B vector. Clear? So we can say theta equal to 0, and whenever we have theta equal to 0, it means we are getting stable position or stable equilibrium. Stable equilibrium. It means what? If you disturb this loop by somewhat amount, definitely again it will come to same situation. Clear? So I can say yes, this part number E, or we can say this diagram actually represent a stable equilibrium position. Clear? Now we are going to discuss last part, and this is part number F. In this part it is given to you, again we have to find value of torque, but directly you can see, if we compare this diagram with previous diagram, only direction of current is changing, all other things are same. It means directly we can say here torque is given by I A cross B. So now we can say here IAB, and this one is what? Sine of 180. Why sine 180? B is acting in upward direction, area vector will be now in downward direction. Clear? So directly you can say here we are having torque, this is equal to 0. Clear? Whenever we have torque 0, it means now we can say what about force? So when torque is 0, definitely I can say net force is also 0. Clear? And actually I can say here one more important information. This is a condition of unstable equilibrium. Unstable equilibrium, because we are getting here angle 180 degree. It means this time this loop is in equilibrium. Let's suppose if you disturb this loop, after some time we can say this loop will never come to its original position or original orientation. Clear? So we can say this is all about this question. Clear? Nowadays student, we are going to solve question number 4.25, and in this question it is given to you a circular coil of 20 turns. Clear? So first of all I am writing here all the parameters. Number of turns, this is given to you 20. Clear? And radius is given 10 centimeter. So value of R, this is given to you 10 centimeter, is placed in a uniform magnetic field of B equal to 0.10 Tesla. Clear? It is normal to plane of a coil, very important. So we can say, let's suppose I am drawing this circular coil like this. Clear? And we can say magnetic field is actually perpendicular to this plane of a coil. Clear? You can imagine this plane like this. Let's suppose this plane is perpendicular to this screen. Clear? So we have magnetic field in this direction. Clear? Now what about area vector? Area vector is always perpendicular to the surface. Clear? Or perpendicular to the plane. So we can say area vector is also in this direction. Clear? Area vector is also in this direction. I can say this is A. Clear? So what is angle between area vector and magnetic field? We can say this is 0. Clear? So in this question it is asking to you what is total torque acting on a coil. So I can say total torque is given by, this is B now, this is sin theta. Clear? Now we can say angle between B and A we have 0. So I can say BI and A, and we can say this is sin 0. Sin 0 value we have 0. Clear? So from here we can say value of torque, this is given by 0 Newton meter. Clear? So value of torque, this is given by 0 Newton meter. Clear? Now if we talk about total force acting on a coil, so I can say F total. Clear? So total force we can say total force acting on this coil. So actually we can say because the magnetic field is acting here in this direction, if we talk about, because we can say actually current is actually all flowing. Yes or no? Yes. We can say it is also given current is flowing in this coil. This is 5 ampere. Clear? So we can say if we talk about magnetic force, because magnetic force will act here in this direction, that one component of force, or we can say one force will cancel other force. Clear? Like this. So we can say net force, or we can not net force, this is acting on this coil, this is 0 Newton. Clear? Now if we talk about average force on each electron. Clear? So if we talk about magnetic field, now we know net force on this coil is 0. Clear? But if we talk about average force, so first I am talking about force acting on each charge. So I can say F is given by QVB sin theta. Yes or no? So because we are talking about average force, so I am saying, let's suppose if I am talking about this charge particle here, so definitely velocity and the angle between velocity vector and magnetic field is 90. Clear? So I can write like this. Clear? So we can also write like this, F equal to EV by EVB. Clear? Now actually my dear student, do you know one relation? We have one relation between current and drift velocity. This is given by I equal to NEA into VD. Clear everyone? So from here we can write like this, value of E and V. This is equal to I by NA. Clear? So we can put value of EV, this is equal to I by NA. So we can write like this, F equal to I by NA and multiplied with B. Clear? I by NA multiplied with B. So now we can say, now if we put here all the values, so value of force I is given 5 ampere, value of B, this is given to you 0.10 and divided by small n. Small n is what? We can say number of electrons per unit volume. Actually we have, it is given here, number of tons. Clear? So this one, okay, let's put it, let's suppose this is n, and area vector. Area is given to you, this is 10 centimeter radius, so we can say pi into, we can say 10 to the power minus 1 whole square. Clear? So now from here you can see, if we talk about density, so this is given, yes, one more term is given to you, the coil is made up of copper wire of cross section area, this one. Clear? So cross section area is already given to you. Clear? So it means directly we can write, so we can say here value that is given to you A, and N is also given 10 to the power 29. This is per meter cube, it means number of electrons per meter cube, and area, this is also given 10 to the power minus 5. Clear? So from here we can say this value is 0.50 and multiply 10 to the power, we can say 24. Clear everyone? So now we can write here value of this force, we can say this is 5 into 10 to the power, or you can also write like this, this is equal to 50 by 100 into 10 to the power minus 24. Clear everyone? So from here we can say value is given by 5 into 10 to the power minus 25 Newton. Clear? So we can say this is average force acting on each electron of a coil due to magnetic field. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 4.26, and in this question it is given to you a solenoid. Listen carefully, actually this is a good question. Clear? In this question it is given a solenoid having length 60 centimeter. So I am writing here length of a solenoid 60 centimeter. Okay, and a radius of 4 centimeter. Okay, radius is also given, it's good, 4 centimeter, fine. Has 3 layers of windings of 300 tons each. Okay, fine. So do you know, whenever a term solenoid comes in our mind, always keep in mind here you have to find number of tons per unit length. Clear? So can we calculate here number of tons per unit length? Number of tons divided by per unit length. But it is also given here we have 3 layers. Clear? So we can say here we have 3 layers, and in one layer we have number of tons, that is 300. Clear? And we have to divide with length. Length of this solenoid is given 0.60. Clear? So from here you can say, we can write like this, 900 divided by 6 by 10. Clear? So we can say this is 2, this one is 3. So from here we can say 10 into 300 divided by 2. So we can say we have number of tons per unit length, this is 1500. Clear? So small n value we can take 1500. Next, it is also given a 2 centimeter long wire of mass 2.5 gram lies inside a solenoid. This is very important. Clear? So we have a solenoid, and inside solenoid, let's suppose like this, we have a solenoid, and inside this solenoid, let's suppose we are placing a very small wire, and this small wire is now connected with the external battery. Clear? So it is given in a question. Clear? So definitely it is given the magnetic field, this is perpendicular to this wire. Okay, fine. The wire is connected through 2 leads parallel to axis of the solenoid. This is clear. External battery which supplies a current of 6 ampere. Okay, in the wire. Clear? It means current is also given, this value we have 6 ampere. Fine. Clear? So what value of current in the windings of a solenoid can support weight of a wire. Clear? So now listen carefully. What value of current in a winding of a solenoid can support the weight of a wire? Now listen. So actually, now you can see whatever number one current is flowing in a wire. Clear? So definitely we can see whenever a current carrying wire is placed in a magnetic field, it will feel a force. Yes or no? So we know that one is feel a force. Clear? And that value we can see given by B. Let's suppose here we have BIL. So let's suppose we can say this is Bill. Clear to everyone? So now we can say let's suppose we are taking that value, that is L dash. Clear? Because this L dash is given to you 2 centimeter long wire. Clear to everyone? So here we have L dash. This is equal to 2.0 centimeter. Clear? 2.0 centimeter. Clear? So now we can say value of magnetic field. So first we can calculate value of magnetic field. This one is mu naught and I. Clear? So value of mu naught, this is given to you 4 pi into 10 to the power minus 7 into number of turns per unit length. This is 1500. Clear? And current that is flowing in a solenoid. So it is given to you no. Clear? So we can say it is not given. So let's suppose I am assuming this is I. Clear? Now we can say we can put this magnetic field in this expression. So from here always keep in mind, here we will put I dash, because this is a current that is flowing in a conductor that is placed inside a solenoid and that is connected with the battery. Clear? So value of B we can see 4 pi into 10 to the power minus 7 multiply 1500. Clear? And we have I. Clear? Now it is multiplied with, now what is current actually carrying? This is 6 ampere. I can say 6 and L dash is given to 2 centimeters. So 2 into 10 to the power minus 2. Clear? Now this is a force that is acting on that conducting wire, and it is also given that which is support. Actually it is given here in this question that winding of solenoid can support the weight of a wire. It means definitely we can say this force that is acting, this force can support, I can say mg. Yes or no? So I can write actually like this. We can say from here you can write like this. This is actually F. F should be equal to mg and this should be equal to 4 pi into 10 to the power minus 7 into 1500 I into 12 into 10 to the power minus 2. Clear? So now we can say, we know what is mass. Mass is given to you. This value we have mass. Where is the mass? 2.5 gram. Clear? So I can say 2.5 into 10 to the power minus 2 multiplied with 10. Clear? I can say 4 pi into 15 into 10 to the power minus 5 into I into 12 into 10 to the power minus 2. We can say this one and this one cancelled out. Clear? So from here can we calculate value of I? Yes or no? So we can easily calculate this value, and this value will come out to be 108.3 ampere approximate, you can say. Clear? So now we can say like this, we can calculate value of a current that is flowing in a winding. Clear? So that it can balance that conducting wire. Clear? So I am again concluding this question. In this question actually one solenoid is given to you. We are placing a conductor inside a solenoid. Clear? So and we are actually also flowing a current in that conductor. So what will happen? Definitely whenever a current carrying conductor placed in a magnetic field, the magnetic field is produced by a solenoid. Clear? So at that time it will feel a force, and that force is the Bill. Clear? Clear? Now that force is actually balanced by the self weight of that rod. So we can say that is equal to mg, and but for that Bill we can say the magnetic field we can calculate by using solenoid. Clear? So value of B we can calculate from that side, and we can finally get value of I. Clear? So this is all about this question. Now dear student, we are going to solve question number 4.27, and my dear student, this question is related to conversion of a galvanometer into voltmeter. Clear? So now concentrate on a screen. In question it is given a galvanometer coil has a resistance of 12 ohm. Clear? So value of capital G, this is given to you 12 ohm. Clear? The meter shows full scale deflection for a current 3 milliampere. Clear? It means value of Ig, this one is given to you 3 milliampere. Clear? Now in this question it is given how will you convert the meter into a voltmeter of a range 0 to 18 volt. Clear? It means now we want to convert this galvanometer for showing the value up to 18 volt. Clear? So let us try to understand mechanism. So let's suppose here we have a galvanometer. Clear? And we can see current that is giving here full scale deflection, that is Ig. So at this time we can see potential difference across this galvanometer we have, this is V equal to Ig and multiply capital G. Clear everyone? Clear? But actually this voltage is comparatively low, we want to increase the range of that voltage. So in galvanometer, if we connect a high resistance in a series, at that time we can say this is actually converting into the voltmeter of a range 0 to 18 volt. How? So let's suppose I am saying now we can actually connecting here a very high resistance. Clear? And let's suppose if we are now measuring potential difference between these two ends and I am getting this is V. Clear? So from here we can say I can write like this, V equal to Ig capital G plus capital R. So how can we convert our galvanometer into voltmeter? So if I connect a very high resistance in a series, then we can easily convert. Okay, so what is our objective in this question? Our objective in this question is to calculate value of resistance, capital R. Clear? So this value we have 18. Clear? Ig value is 3 milliampere. We can say capital G, this is 12 plus R. Clear? We can say this one is 6. So 6000, this should be equal to 12 plus R. So from here we can say external resistance that should be connected 1000 minus 12. So I can say this is equal to 5988 ohm. Clear? So we can say this is value of capital R. Clear to everyone? So capital R value is given to you 5988 ohm. Clear? So this is value capital. Clear? So like this we can convert galvanometer into voltmeter. Clear? So this is all about this question. Now dear student, we are going to discuss question number 4.28, and in this question it is given to you this is a question related to galvanometer and conversion of a galvanometer into ammeter. Clear? So always keep in mind, whenever you want to convert a galvanometer into ammeter, definitely here you will attach a shunt resistance, means a resistance in a parallel to galvanometer. The value of the shunt resistance, it should be very small. Clear? So now let us try to solve this numerical. In this question it is given a galvanometer coil has a resistance 15 ohm. It means value of capital G is given to you 15 ohm. Clear? The meter shows a full scale deflection for a current of 4 milliampere. It means I can say Ig, this should be equal to 4 milliampere. Clear? How will you convert the meter into an ammeter of range 0 to 6 ampere? Clear? So I can say here, let's suppose I am saying this is galvanometer. Clear? Current that is flowing in this galvanometer, that is Ig. This is known as full scale deflection current. Clear? Now let's suppose if I connect a shunt resistance that is in the parallel of this galvanometer. Clear? So let's suppose this is S. Clear? So I am assuming, let's suppose I want to increase range of a galvanometer. So let's suppose current that is flowing here, the capital I. Out of the capital I, Ig current is going in a galvanometer. So we can say here, we can write this is I minus Ig current is going through shunt resistance. Clear? Now we can say potential difference between these 2 points is always remain same. So I can say we can write like this, IgG, this should be given by I minus Ig and multiplied with S. Clear? So now we can say Ig capital G, this is equal to Is minus Ig capital S. Clear? So now what is our objective? Our objective in this question is to calculate value of shunt resistance. Clear? So we can write like this, value of shunt resistance, this is I minus Ig and this is equal to Ig multiply G. Clear? So we can say value of S, this is given by Ig capital G divided by I minus Ig. Clear? Okay, value of Ig. Value of Ig we can say this is 4 milliampere. So 4 into 10 to the power minus 3 into capital G. capital G we can say this is 15 ohm, so this is 15 and it is divided by, I can say I minus Ig. I is given to you, we want to convert in 6 ampere and Ig is given 4 milliampere, means 0.004. Clear? So from here we can say, we can write like this, this is 4 into 15. Clear? Actually I am dividing with 10 to the power minus 3 in numerator and denominator both. Clear? I can say here we can say this is 6000 minus 4. Clear? So now we can say if we calculate value of shunt resistance, we can find here this is value 60 divided by 6000 minus 4. Clear? So from here you can say we are getting value 60 divided by 5996. Clear? So now if you calculate from here, you will find approximately this value 10 milliohm. Yes or no? So from here you can say actually we are getting a very small value of a shunt resistance. Clear to everyone? So correct answer of this question we have shunt resistance 10 milliohm, and this is all about this question. Clear?